Next up, we have oral presentation 10 in Arundel County, Maryland, and they're presenting a Mission 13 flight experiment.
I'm Gabrielle Munoz from Magothy River Middle School, and my experiment is the effect of microgravity on the structural strength of concrete. The purpose of my team's experiment was to determine if concrete made in microgravity can hold its natural structural integrity. Structural integrity is the ability of an item to hold together under a load without breaking or deforming. We're testing to see how much weight the sample of concrete from microgravity will hold. On Earth, mixing concrete is accomplished by mixing and setting with the help of gravity. But we want to find out if concrete will hold up with little to no gravity. Our findings could provide insight into how concrete can be used in the microgravity future. We found that concrete is the single most widely used human-made material in the world. Concrete is a mixture of paste and aggregates. The paste, composed of Portland cement and water, coats the surface of the fine and coarse aggregates. Through a chemical reaction called hydration, the paste hardens and gains strength to form the rock-like mass known as concrete. The concrete mix we're using, Quikrete, is 60% limestone, 25% silica, and 5% alumina, iron oxide, and gypsum. From our pre-sending tests, we found that the key to achieving a strong, durable concrete rests in the careful proportioning and mixing of the ingredients. Our team spent several weeks testing different ratios of tap water and concrete powder to achieve solid concrete samples in the FME. When we used only 1 milliliter of water with our 12.6 grams of powder, it was very powdery and it wasn't solid. When we used 12.6 grams of concrete again and 2 milliliters of water, it was very brittle still and had many cracks and holes. We couldn't fit it with 12.6 grams and 3 milliliters of water, so we had to take it down to 8 grams of concrete and 3 milliliters of water. We'll be using a Type 2 FME mini tube to create the concrete sample. We'll use small plastic funnels to pour the tap water on one side and the concrete mix on the other side. Volume 1 will be 8 grams of the Quikrete concrete powder with a pH of 12 to 13. We're going to get this from a 40-pound bag of ready-to-use Quikrete concrete mix. Volume 2 will be 3 milliliters of tap water with a pH of 7. Our requested crew interaction would be on the first day that it arrives to unclamp Clamp A and shake vigorously for 2 minutes. After that, we would just like the astronauts to let it sit and set. When the experiment returns to us, the concrete will be observed and tested. Our team will use different weights ranging from 10 grams to 1,000 grams or more in order to test the strength of the concrete. Our experiment setup will simulate a bridge-like structure where the cylinder piece of concrete will be laid in between 2 desks. We'll tie one end of the string to the concrete and the other tied to a separate weight. We'll test how much weight it can hold before it cracks or eventually breaks. The test results will then be compared with the test results prior to the ISS launch to see how microgravity affects the strength of the concrete. I'd like to thank everyone for their time, and I hope that you guys have a nice day.
Hi, my name is Luis Munoz. I'm from Arundel County as well. I'm the father of this microgravity researcher. And I just wanted to know if you guys had a hypothesis for what the effects of microgravity would be on the sample that you're getting back in the space station.
My team hypothesized that because there's no gravity to hold it together, that the particles would kind of be more spread out and it wouldn't be as strong or composed.
Awesome. Thank you very much.
My name is Dave Camara from Wisconsin. My question is, why did you start with 12.6 milliliters?
We figured if we had more concrete mix that we'd get a larger sample, but we soon figured out that it wouldn't set because it didn't have enough water and it wouldn't fit all in the tube.
Thank you.